Okay, so we ended on Thursday with a little discussion about how you can use your calculator to find a definite integral. Now, the question becomes then, well, when can I use my calculator? You can use your calculator anytime it says you can use your calculator. However, sometimes it will say show an antiderivative. It's commonly called fn_int. fn_int will not show you the antiderivative. It will just plug and chug and give you an answer. Okay? So most of the time, if you have your calculator or it's a calculator portion of a test or an exam or the AP test, then fn_int the snot out of everything. But again, if you don't have a calculator or it says to show an antiderivative, you're going to have to do it by hand. Okay, so that's where we left off. Next thing, this is a fairly big concept. And it goes something like this. We can redefine the integral as an area accumulator. What does it mean to accumulate? Build up or gather, correct. So that integral as an area accumulator, because you know it now as the area under the curve, but we're going to change it a little bit, comes up in a problem like this. So you'll notice that I gave you a picture of f of x. And then I said, okay, great, but we have this other function g of x. And g of x is defined as the area under the curve of f of x from 0 to x. Are you with me so far? Audience participation part of the program? Yes? Yes. Beautiful. So let's see if you're with me. What's g of o? What's g of o? Holy smokes. What's g of 0? Why? Bingo. We have that as one of our properties. Anytime you go from a to a for an integral, the area under the curve will be 0. Okay, what's g of 3? Okay, well, what does this mean? G of 3 means what happens when you plug x in, or 3 in for x. So I'm wondering, what is the integral from 0 to 3 of f of x dx? And so what we're doing is we're starting at 0, and we're starting to accumulate area as we move over towards x. So one way to think about it is stacking a bunch of sticks. And we just keep going over. This is getting tedious. We should have done it for 1 till we get to 3. Okay. So what's the answer? Let me get rid of the mess here so you can see. 7. Why? One, 2, 3, 4, 5, 6, 2 halves, 7. Love it. What's g of 9? By the way, before we answer that, will g of 9 be bigger or smaller than g of 3?
Small.
Why, Conrad?
Because it goes down into the negative, so the area is going to decrease.
Good. And answering these questions, you can be a little bit sneaky with it and save yourselves a lot of hassles. So notice that this triangle is the same as that triangle. Therefore, I don't need to worry about either one of them because they cancel each other out. So we're 7 up to here because we did g of 3. And then we've got this guy over here. Well, what's that guy? That's a trapezoid. What's the area of that puppy? 2, 3, 2. What is it? 5. But it's negative 5. Because as Conrad said, we're below the x-axis. Therefore, g of 9 would be 2.
Will you ever be asked to find g of o or g of 3, any of these without a picture like this, or no?
You'd have to be given some type of information. These types of problems normally are accompanied by some pretty geometric picture where you've got triangles, rectangles, squares, trapezoids, that kind of stuff.
Okay.
Okay, go.
I think you said it, but I didn't catch it. Why don't you count everything before 7 too? Like x equals 7.
Oh, these guys, the shaded things?
Yeah.
Because they cancel out. You see that these areas are the same, right?
Yeah.
But remember, we defined anything below the x-axis as being negative. So whatever that area is, I'm not going to bother finding it because that's going to be the exact same, and it's going to cancel each other.
Okay. Thank you.
Okay. Now I could have just said, okay, 7, then find the area of that triangle, then find the area of that triangle, make it negative, then add negative 5. But again, if you're shifty about it, you can save yourself some hassles.
Okay.
Okay. Everybody else good to go? Beautiful. Now the fun one. Where does G have a maximum? Why?
Because that's the point where the sum of all stuff before it is highest.
I'm sorry, what?
At 5, the area under the curve is the greatest.
Why?
Because it doesn't get any higher on the graph and it's not being subtracted from.
Okay.
Is it when, I don't know if it's f of x, the g of x changes from positive, I guess it'd be f of x changes from positive to negative?
It would actually be G of x.
It's g of x,
Yeah.
okay.
Oh, no, sorry, you're right, f of x, because it's a derivative.
Yeah, because
Yeah.
that's the, yeah.
Okay, so now we have a couple different ways. Let's address Matthew's statement first. He said it's 5 because it's where all this area is positive, then it starts to become negative. So this is where we bring the idea of an area accumulator into this problem. As I start at 0 and I start moving to the right, I'm adding positive area. I continue to add positive area until I hit 5. After 5, I start adding negative area. And notice I use the term adding negative area, not subtracting area. Because I think it makes more sense to talk about adding negative versus subtracting. Okay. Then Lily said something about it being where f changes from positive to negative or negative to positive.
Well, originally I said positive to negative. and I
You're
think that's
correct.
still
No,
right.
no, it's
Okay.
positive to negative. Yeah. So here's the other approach. Forget about this problem. Let's suppose I gave you a function h of x. How would you find the max of that function? By the way, you've done this like a billion times. How do you find the max of a function? How do you find the critical numbers?
When set it equals 0,
Setting what equal to 0?
the function.
No.
The derivative.
The derivative. Set the derivative equal to 0, find the critical numbers, test regions. Okay, so that means if I'm looking for a max of g of x, I'd have to take the derivative of g of x. What's the derivative of g of x?
F of x.
Good. G prime of x is equal to f of x. What's g double prime of x?
Prime.
F prime of x. Okay. So we go back to what Lily was saying. She's, well, because f changes from positive to negative, that allows us to find the maximum of g of x. Well, that's true because we would take the derivative of g of x to get f of x. Ouch. It's probably not a good thing when you get shocked by the display and then all the other TVs go out. And now I can't remember my middle name. This is bad. Okay, so taking the derivative of g of x, we get f of x. A critical number would happen at 5 because that's where the derivative of g changes from positive to negative. Perfect. That same idea would apply for the minimum. Where's the minimum? Say again? That question is easiest to answer by thinking of it as an area accumulator. So I start at 0 and I start moving to the right. I'm adding positive area, adding positive area, adding positive area. I hit 5. We start adding negative area. In order to get a minimum, I would have to add the most negative area. Where does that happen? 9. Very good. Ooh, that's a pitiful mind. There we go. Okay, does that make sense? This is a very common type of problem. One function represented as a graph from another function using the integral versus the derivatives, which we did in the last chapter. When you see a problem like this, one of the first things you should do is this. List the relationship between all of the derivatives. I know that g of x is the integral, therefore g prime is the function. I know g double prime is the first derivative. So we could go back, if we had more time, and figure out where the point of inflections are. That would be fun. We're not going to do that now. We'll come back to that later because I'm sure these are going to pop up in the homework. Okay? Question, Mason?
Why isn't the minimum 0?
Oh. So why would you argue it's at 0?
Because the total area would be 0, and at 9 it's 2.
Huh. Can you have a minimum at an endpoint?
No.
Oh, wait, hold on. Are you sure? Quick review. Can you have a local or relative min at an endpoint? Yes. Can you have an absolute at an endpoint?
No.
No. Well done. Now, what if
Could it be either? Because it doesn't specify if it's absolute or.
you're arguing they're both minimums?
Well, I could. I don't know, I'm confused why it would be one and not the other.
It could be both. Because they're both endpoints, it doesn't matter. Now notice, however, if this region, let's call that region 1, was bigger than region H, I don't know why that happened, H with a hat and a bottom on it, then the minimum would have to be at the right endpoint. Because that would be the place where there's the most negative amount of area. Okay. We're going to skip this. We'll get to the other one later. We'll come back to displacement later on. Let's go to, get rid of that guy, and go to this guy. Just keep plugging along. Okay, there's a math joke for you. One. Stop. Get it? Yeah? Are you sure you get it? Yeah?
There's no. I'll admit, I'm good at aspirate, and then you have to add.
What the heck is
You have to
aspirate?
add 1 to the. I've never heard of
aspirate.
power
What is aspirate?
n. Because at the end it's
I don't
equal
know.
to 0, so then it becomes n to the first, then it's aspirate n aspirate.
Does everybody get the joke?
No, I got it.
What variable, or sorry, let me rephrase the question. What's my variable in this case? N, because it's dn. Because n is my variable, this is a constant. What's the antiderivative of a constant? No.
Oh, one.
Antiderivative. In other words, what's the antiderivative of 2dx? 2x. Therefore, what's the antiderivative of aspiri? dn. Aspiri n, which is aspirin, but it's an indefinite integral, so we have to include a plus c. Get it? Okay. Wait. Let's make sure you do understand what's going on. What if I ask you this?
I don't take aspirate. Aspirate n squared.
I didn't do it.
Yeah, that's what I thought. An aspirate and square.
Say again?
plus-
Beautiful. What's that? Well, this is a constant. So we're taking actually the integral of n dn. Raise the exponent by 1, multiply by the reciprocal. Yep.
I was just doing this is all mushed together.
I understand.
Aspirate.
Aspirate. Plus C.
Okay.
Okay. More fundamental theorem of calculus. So now we have the mean value theorem. This is very conceptual. But I have a pretty good example that I think will help you understand. So here's the idea. I'll let you read that. Let me know if you have trouble with any of the words.
Okay.
Scraggy.
It's a word.
So what is it? I don't
If it's not a word, I made it up, but you understand what I mean. All right, you understand the scenario here.
Yes.
Yeah.
What happens when the ice melts? Josie, what does this mean? Will that level be higher or lower than the top of the ice? Lower? It can't be above the top of the ice? No, it's got to be below, right? Okay. This is what I think is a pretty good example of how the mean value theorem says. How the mean value theorem works. So our function is going to be the ice. There's our function. My interval are the sides of the glass. So the sides of the glass are the A and the B. Inside there I have the function. The function extends outside the glass a little bit. Deal with it. When that function melts down, it's going to find some leveling point. That leveling point becomes what's called the average of the function. Now notice that I've got some area above and I've got some area below. How does the red area compare to the blue area? They're the same, correct. Which goes back to the original question, can the water level be above the top of the ice? No, because it's got to be an average value. There's got to be an equal amount of space below as there is above. Our goal in this scenario is to find that level, which again is called the average value of a function. And notice when it melts down, it makes this cute little rectangle. How long is that? Good. How tall is this? Say again? F of z. Okay, which is what I called the y value where that thing melts down. So if the red area matches the blue area, then the area under the curve has to be the same as the rectangle. Are you with me? That's exactly what the mean value theorem says. Okay, so the average value of the function is that f of z thing. And if we can find f of z, we can find the area under the curve by using a couple different methods, which I'll get to in a second. Now, the other thing I didn't talk about, and I only highlighted one of them, But you'll see there's a spot where our average value goes through some of the ice, and it hits the ice in a couple different locations. I just highlighted the one on the right. There's another one on the left. That's called the Z term. That's the X value where it hits the average level. Okay? We're used to going this way, taking an X value, going up to the Y value, and coming across to find that value. We're going to go backwards. We're going to go from the Y value down to the X value.
It's like, so like the beta A, is that saying like what length of a glass is what meets that?
The width of the glass. Yep.
Okay.
Okay.
But
Everybody?
aren't we keeping the same glass? Oh,
We are, the whole time. That's not going to change.
okay,
What's going to change is what we're looking for is f of z.
okay,
You'll be told the width of the glass.
okay.
Okay? So there it is. It's got to be continuous. We have to put that in there just to keep everybody above board, but it's got to be continuous, otherwise it doesn't make any sense. And so the left half of this is what we already know. Area under the curve from A to B. The right-hand side is the area of the rectangle. The area under the curve is going to match that average value by melting down. So MVT is frequently referred to as the Meltdown theorem, because you're taking a function and melting it down to find that average value. There's only two variables in that. I don't even know if you call them variables. There's only two things to play with in that equation. F of x and f of z. If you know one, you can find the other. Because you should know by now how to take a definite integral. Okay, so here we go. By the way, I don't like this form, so I just rewrote it this way. It's the same thing. I just divided both sides by 1 over b minus a. It's the same thing. And I changed f of z is the traditional way to do it. I like f of av because it reminds me that it's an average value. If you want to go back and use the other one, that's okay.
AV is one thing. AV is one thing.
Yeah, it's just a notation.
Okay.
Actually, this would probably even be better if I thought about it.
Yeah.
Average. So you don't get confused with Avery or avocado or avalanche or avant-garde or
Availability.
any others?
Availability.
Availability, thank you. And avenues. And
No street.
I almost said eventually, but that's
Average.
That's bad.
that's why I went into math. I'm not really good with words.
Advantageous.
Okay, so here we go. I've got a function x cubed.
No way is that real. No way is that real.
I don't know about that.
I saved you a lot of the work.
Oh, it's done.
I knew you could do this, but I wanted to save time and do it for you. I know that the area under the curve from 0 to 4 of that cubic function is 64. So for those,
0 and 4, right?
what am I waiting for?
Oh.
You good? Okay.
Oh, okay.
For those of you, I don't remember if I have a picture or not, so I'll just draw one. Okay. So, somewhere along here, from 0 to 4, there's a horizontal line. And the horizontal line would be drawn in such a way that everything above the horizontal line up to the function would have the same area as everything below the horizontal line down to the function. So I'm going to guess something like, I'm going to go with this. Maybe? I don't know. Does this area look to be about the same as that area?
Yeah.
It's good enough for
Why
this
not?
job. Okay, that's what we're going to go with. So this is my f of z value. This rectangle is 4 times f of z. The area under the curve has to be the same value. So the integral from 0 to 4 of x cubed dx has to be equal to f of z times 4. Okay, or the other way I did it on that second slide was I said f of average is equal to 1 over 4 times the integral from 0 to 4 of x cubed dx. These are the exact same thing. Notice I just divided both sides by 4 and changed f of z to f at. Or avg. Good. Avg? Avg. It's a g, right. This I know, 64. Will you still love me when I'm 64? So f of z is equal to 16. Woohoo! Questions so far? Not difficult, yes? Correct? Good. As I said, we're going to go backwards. I know that this is at 16. I want to go backwards to find that point, which we commonly call z. How? Go.
So you can put 16 in now for f of z, and then it'd be 4 minus z instead of 4. I don't know if that's right.
Overthinking it.
I am. Do you just put z in?
You can't plug z in.
Oh.
We're looking for x, right? Or, well, we're looking for z, which is an x value. So how do I find out where that is? Alice?
Don't you just take like the original equation of x cubed and you set it as 16 equals x cubed?
16 equals x cubed, or put 16 into x cubed?
16 equals, because 16 is the y value.
Want to help me out there? What's the cubic root of 16?
What is it?
2.52?
Yeah.
Well, we should round to 3 decimal places. 2.220. 2.520.
Wait, is that that's it too?
Yeah. Good job. That was supposed to be preguntas in Spanish, but it came out as preguntas.
Okay. So do you write it as x or do you write it as z?
Well, you can do either one.
Okay.
I do this all the time. I slip into a weird notation there, but yeah, it's z and x in this case are the same. It is possible to get more than one z value. Notice in this picture, the horizontal f of z value only hits the function once, so I only have one answer. If I go back to this guy, I would have 2 answers. It depends on the problem. Good? Questions? Oh, look, there's all the work. What do we get? Let's see. Oh. Uh-oh. Oh, I rounded wrong. Well, that's okay. Here's how I defend myself. On the AP test, you can either round or you can truncate. Now I remember, I chose to truncate here.
Yeah, sure.
All right.
Sure you
Believe you.
Be fine. It's okay. It's all right.
Nice try making up fake words.
Truncate. It's a real word.
That was fake.
Okay, we're done. That's it. Yeah, just one MVT, that's it.
Fundamental theory.
Oh. I'm glad I don't own that shirt. It caused me to scratch.
What are you making a judgment for anybody that owns that shirt?
Yeah, I would be distressed if I owned that shirt.
What if somebody else owned that shirt?
Well then, if they're mad at that shirt,
I didn't say that.
theoretically.
I'm just trying to get a feel for where Lily's at with anybody that happens to own that
I'm not
shirt.
gonna judge someone for their shirt.
You're just saying you
If
yourself.
it was in my closet, it would like haunt me.
I understand. Right, you'd hear it called to you late at night.
Yeah,
Right.
my closet door would like creak open.
You can never leave your closet open at night because the closet t-shirt monster would get you.
Yeah, yeah.
Uh-huh.
I'm not even think your monsters in my closet because my dress is way weird.